Good afternoon, ladies and gents. Jamie here. Still a few people logging in, so we'll just give it a couple more minutes before we kick off. Okay. Good afternoon, ladies and gentlemen. Welcome to this third installment of our webinar series. Myself, Jamie Pegg from Excel Point, and Ali Batour, our Business Development Manager for Australia, and Christoph Hayert, our Applications Engineering Manager, who's going to be doing the heavy lifting on this webinar. Hopefully you guys have all received the URLs to point you to the recorded sessions, the first two recorded sessions. In terms of asking questions and things, same as the last two times, if you can please use the Q&A chat window. If for some reason you haven't received the URL for the previously recorded sessions, then if you'd like to just let us know via the Q&A chat window, and I can arrange that separately. And then lastly, before Christoph kicks off, this is quite a detailed session, and going to be spending some time with the previous sort of material, along with Petalinux and building an operating system. But it's at this point, I'd like to just, I guess, set everybody's expectation that we're not embedded Linux gurus. So bear with us if you've got questions that we can't answer. We will endeavor to come back to you on those. But yeah, certainly please feel free to still ask questions and we'll do our best to answer. This session will last approximately an hour, possibly a little more. And yeah, we'll be doing the same thing. We'll be making the recording available afterwards. So yeah, over to you, Christoph.
Thanks, Jamie. Hello and welcome everyone again to the final session of the webinar series around the ZYNQ UltraScale Plus MPSoC. So just to recap, during the first session, we built an MPSoC system using the IP integrator within the Vivado design suite, generated a bit stream and exported that hardware. During the previous session, we used that generated hardware in the Vita software development kit, built and ran some very basic applications on both an A53 processor as well as a R5 processor. So today we'll use the same generated hardware again, but this time we'll use it to build an embedded Linux system, which will then boot on the same ZYNQ 102 evaluation board that we used during the last session. What we can also do is add an application to the root file system, which we can then execute once Linux is booted. And we can also briefly show you how you can develop Linux applications using the Vitis software development kit, using information generated or boot components generated by Petalinux. But before we do that, like last week, we'll start with introducing Petalinux a little bit first. Although it's not entirely clear in this diagram, so this area here involves using the Petalinux tools in order to generate all the required Linux components for deploying an embedded Linux system. So during the first session, we went through this system hardware design. During the last session, we went through some system software development, and then today we'll build some Linux components. And again, here you already see there is a little bit of overlap between Vitis SDK and Petalinux. As you'll learn during the session, some of the tools used by Vitis SDK as well as Petalinux are the same. So these are bootgen, there's a scripted command line interface, etc. So we'll discuss this a little bit further. So let's get this final show on the road. Petalinux is an embedded Linux software development kit targeting FPGA-based SoC designs. It's a development and build environment that automates many of the tasks to boot embedded Linux on ZYNQ devices. It provides you with an easy and fast way to develop, build, and deploy Linux-based software on ZYNQ 7000 SoC devices, ZYNQ UltraScale Plus, MPSoC devices, ZYNQ UltraScale Plus RF SoC devices, as well as Versal ACAP devices. Note that the Petalinux is available at no charge, but also note that it does not deliver or create a Linux distribution as such, but it provides a place for configuration of all the Linux components. It also provides integration with the other tools such as the Vivado Design Suite and the Vitis Unified Software Platform. Furthermore, it allows you to work easily with available software from GitHub and other open source communities. The Petalinux tools include features such as command line interfaces, application, device driver, and library generators, and templates, a bootable system image builder, GCC tools, an integrated QEMU system simulator, and support for automation and debugging tools. Now, for many years, Petalinux used a proprietary build system, but has since moved to the Yocto project under the hood for configuring and building various components. So Petalinux works as a sort of Yocto wrapper. That is, Yocto is the underlying low-level build system for Petalinux. It uses the standard Yocto bitbake tool to build the entire system, including the kernel, root file system, and U-boot. This Yocto framework operates on a layer concept, and these layers are controlled by configuration files referred to as recipes. So if you've gone through the documentation for Petalinux, you will probably have heard about recipes. A minimal downloads feature enables you to explore the Yocto predefined settings, which configure the various Yocto features for a given project. A key Yocto parameter here is the pre-mirror URL for downloading the source code of components. So when you build Linux for the first time, Petalinux for the first time, it takes a bit of time because it needs to download the source code for those components. The Yocto extensible SDK contains multiple Yocto layers such as core and other popular layers such as Meta ZYNQ, Meta ZYNQ tools, Meta Petalinux, and Meta OpenAmp. The Meta ZYNQ layer provides additional support for Yocto Open Embedded, adding recipes for various components. The Meta ZYNQ tool layer supports all bare metal components from ZYNQ. Meta Petalinux is a distribution layer that provides all the supported packages used by the Petalinux tools, including the toolchain. And ZYNQ provides a set of recipes in the Meta Petalinux layer that define the components and behavior of the default Petalinux system, which includes a minimal and full feature configuration. And then finally, Meta OpenAmp layer provides support for building libmetal and OpenAmp libraries. Apart from this, Yocto also implements shared state cache, which supports incremental builds. So that means that the results of each portion of the build are stored and can be reused. So the second time you modify a component, it doesn't need to download that again using this pre-mirror URL. Petalinux then, on top of that, Petalinux includes utilities that are not found in the Yocto toolset, and this such as the scripted command line tool and the ZYNQ debugger, a device tree generator, and other tools used for build and deployment. The tool chains used by Petalinux are based on GCC and Linaro external tool chains. Petalinux uses XSCT underneath, so that interactive and scriptable command line interface, which supports creation, configuration, as well as building all the common software projects. And it also, as mentioned, includes the ZYNQ system debugger. If we look at the workflow to build an embedded Linux system using Petalinux, we can see that it follows a sequential design flow model. The same exported hardware description, the ZYNQ support archive, which we previously used to build software applications with Vitis IDE, can also be used by Petalinux for software configuration and builds. So the hardware specification, the settings in the hardware specifications are propagated to the software configuration when creating and configuring a Petalinux project. Then the kernel, application, and system settings are configured, and the final Linux system image is built. Once the image is built, it can be booted on the target platform, and finally the desired application is deployed, executed on the target. Petalinux provides a command line utility to perform all these actions, and so Petalinux is very much command line. So it's not a GUI-based tool, it's all command line driven. And if we look at a summary of the steps involved, there are a number of commands that need to be executed. So first, the Petalinux project is created using the Petalinux create command. The project is then initialized using the Petalinux -config -- get hardware description command. So during the project initialization or update, Petalinux then generates a device resource file and U-boot configuration header files and enables the Linux kernel drivers based on that hardware description file. The system level options for the Petalinux project are then configured using the Petalinux config command. The Linux kernel is configured using the Petalinux config-c kernel command. The root file system using the Petalinux config-c root fs command. And then the entire system is built using the Petalinux build command. The package for deploying the system on the target platform is generated using the Petalinux package command. And finally, the system is booted for testing using the Petalinux boot command. We'll go through these in more detail shortly, but this is just a high-level overview of the steps involved to build the system. So let's have a look what comes into and what comes out of the Petalinux tool. So the input is either the hardware specification file or a Petalinux installation BSP. So regardless of how that hardware platform is created and configured, there are a small number of changes required to make the hardware platform Linux ready. During the project initialization or an update, as mentioned, Petalinux generates a device tree, then U-boot configuration header files, and enables the Linux kernel drivers. Petalinux BSPs, they are reference designs on supported boards for users to start working with and to customize your projects. And they come in the form of an installable BSP file and include everything, all the necessary design files, configuration files, which are pre-built, tested hardware and software images ready for deployment on the board. So they're not included with the Petalinux installer. So you'd need to download these separately if you're working on a particular evaluation board. Upon project creation in Petalinux, it will generate a project layout. So let's have a bit of a look at what this looks like, because it can seem a little bit daunting and convoluted at the start when you start navigating through this directory structure. So let's explain it a bit. So the project spec is the main directory, and it's the name you provide in creating the project. Then you'll see a number of subdirectories. The configs directory consists of the config and rootfs config subdirectories. The config directory contains the overall project configuration, whereas the rootfs config directory contains the file for the root file system configuration. The hardware description directory contains hardware-related information. And the meta user directory contains another 3 subdirectories: configuration, recipes apps, and recipes BSP. The configuration directory contains layer.conf, Petalinux bsp.conf, these 2 files. Layer.conf contains layer configuration, and Petalinux bsp.conf starts off empty. Recipes apps contains the GPIO demo and the Pika poke directories, and recipes BSP contains the device tree and U-boot directories. The meta user layer is a placeholder for all user-specific changes. So it has the customized bitbake append and configuration files. So a BB append file is used for appending metadata information to a recipe. But not one note to make here is that in order for that BB append file to be successfully appended to a recipe, it must have the same name as the recipe that it is extending. When the hardware is then imported, the project layout changes and 2 top-level directories, build and components, will have been added. The project spec is also, no, that's not, I actually had to change this diagram. There was something wrong in this diagram, and one of the older directories that used to be generated is not generated anymore. So I can actually skip that. Where am I? Recipes BSP. Yeah, so the build directory is reserved as the Yocto build area. It contains also another subdirectories. And the files in this layer, though, should never be updated as they are generated by the Petalinux commands. So this is when you import the hardware. So there's some details. And then finally, with the project created and you have the hardware added, the project can be built. Once the project's built, the directory changes again, and it's shown here. And here you can see that 3 more directories have been added. Images, which contain all the bootable images for the Linux subsystem. And if a BSP was used for the generation of the project, then it will populate a pre-build directory. And the rest, I think, is about the same. So let's delve into each Petalinux command a little bit deeper. So the first command we'll use later on to build the embedded Linux system is Petalinux create. The Petalinux create command is used to create a new Petalinux project or a new component within a specified project. And you have a number of options here that can be used along with this command. The -t or ~type option selects type, which can be a Petalinux project, a Linux user application, or a Linux user module. The -n or ~name option specifies the name of the project or component. The -p or ~project option specifies the full path to a Petalinux project. This option is not used for project creation as the working directory is taken by default. The ~template option specifies the template. For project creation, the templates available are ZYNQ for the ZYNQ UltraScale Plus MPSoC, which is what we'll be using, ZYNQ for ZYNQ 7000 devices, and Microblaze for the Microblaze processor. When an application is created, the templates available are C, C++, AutoConf, and Install. The -c or ~source option specifies the valid source format. The ~enable options enables a specific component. and the /4 option overrides the existing settings. So here on the right-hand side are a number of examples on how to use this command. And we're interested in the second one here. So because we've built some hardware for an MPSoC, so we're going to create a project using this template, and then afterwards also create and enable an application. If we have time, we can maybe cover how to enable and add some custom kernels or libraries or pre-built libraries to the root file system as well, but we'll see how we get on. The Petalinux config command configures the Petalinux project order component in the menu config interface. The --get hardware description is the command. It imports the hardware description in the project. So it needs a path to the XSA directory from which the hardware is imported. So this is the XSA which we had exported in the Vivado design suite. Once the hardware is imported, the project is initialized or updated to reflect the hardware configurations. And the components affected by this process can include the first stage bootloader configuration, U-boot options, Linux kernel options, and the Linux device reconfiguration. The -C or -- component option specifies the system component and configures it. If no component specified, it performs a top-level project configuration. The -P or -- project option specifies the full path to the Petalinux project. The -V or -- verbose option displays additional output messages. The --dev config option initializes the Linux kernel or U-boot configuration using the specified dev config file. And the --silent config option restores the prior configuration. So again, here are a number of examples of how to use the command. So we will be importing our own generated XSA file using this command, and then we'll build all the individual components. You don't always have to do that. If you build the kernel, for instance, then it will update the device tree and U-boot, so it's kind of incremental. So the Petalinux build command builds the entire system, the Linux embedded system, or a specified component. And it uses the Yocto project underneath and calls bitbake when the command is invoked. So the first time, this process can take a bit of time. I would even say up to an hour or an hour and a half. So what we'll do today is we'll kick off this command, but then I will need to cheat a little bit because we don't have time to wait for it. I'd already pre-built this today. So, but we'll go through each individual step. But then while this is building, we'll actually use the generated components. So the -C or -- component option specifies the system component to be built. Again, the -P or -- project option specifies the path to the Petalinux project. The -X option executes specified build steps using bitbake. The -V or -- verbose option also displays additional output messages. The -S option builds the Yocto SDK, which is optional. And the -B option executes tasks from a specific .bb file and builds the components, ignoring the dependencies. Also here on the right-hand side, again, a number of commands on how to use this. So the first one would build the entire system, but then you can also build individual components such as the kernel, the root file system, or U-boot, etc. The Petalinux package option, a command packages a Petalinux project into a format for deployment. So this is the final step before booting the image. And the tool here provides several workflows whose operations vary depending on the target package format. So the supported formats are boot, BSP, image, pre-built, and sysroot. So the boot package type creates a .bin or .mcs file that allows the target device to boot. The BSP package type creates a BSP file that includes the entire contents of the target Petalinux project. So this allows you to export and reuse the BSP for a future project perhaps, that you can then reuse, just as you would have a BSP for an evaluation board, for an AMD evaluation board, you can generate your own BSP as well. Image package type packages the image for the components with the specified format. The pre-built package type creates a new directory within the Linux project called pre-built, and it contains pre-built content that's useful for booting directly on physical boards. This option is typically used as a precursor for creating a BSP package type. And then finally, the --sysroot option installs the sysroot for the Vitis software platform. It can specify the installer path, and it can also install the directory path. Again, here are a number of examples on how to use these commands. So the first two commands generate a bootable image that can be used directly on a ZYNQ UltraScale Plus MPSoC device. And so we'll be using some of these while we build. The Petalinux boot command boots microblade CPUs, ZYNQ SoCs, ZYNQ UltraScale Plus MPSoCs with Petalinux images through JTAG or QEMU. So it provides two distinct workflows. In the first one, using the Petalinux boot --JTAG option, images are downloaded and booted on a physical board using a JTAG cable connection. And in the second workflow, images are loaded using the QEMU software emulator. There are some other options here as well, but we won't elaborate too much on that here. So because today we will actually not be booting over JTAG. Again, depending on the image, it can take a few minutes, so I don't want to stall the session. So we'll actually be booting via SD card today. There are a number of ways to create Linux user application. So now that we're talking about Petalinux, let's focus on how you can create and customize a user application using the Petalinux tool. So after the execution of the first command, a new user application named My App is created, and a new directory is also created. So this My App, we call it My App here. This My App directory stores all the template generated files, including a single application template, and it also includes a makefile for cross compilation. You can create a new application and then also enable it in the root file system using the --enable option, but you must ensure that the binary data when you do this, you must ensure that the binary data being installed in the target file system is compatible with the underlying hardware implementation of your system. So in order to add the application to the root file system, it's when configuring the root file system using the Petalinux -config-c rootfs, you can go into its directory, and once you've created and enabled the app, or added the app, you can enable it in here. And then once it's added to the root file system, you just perform a regular Petalinux build, and you should find your application in the user.bin directory, and then you can just run it as shown here. Another more user-friendly way to develop Linux applications is by using the Vitis IDE. And this is a quite simple diagram, but I think it's really, really great because it shows you how the three tools interact with each other. Now, I don't want to claim the fame. I actually did not generate this diagram, so just for your information, I'm not claiming any fame here. But on the top left, we see that we'll need to use the customized hardware also here. So this is made available to both Petalinux and Vitis IDE. Petalinux is then used to develop and build the Linux-based project using the Petalinux create, Petalinux build, etc. commands that we've been discussing up until now, and which then generates the device tree blob, the first stage bootloader, U-boot application, a Linux kernel, root file system, and all the components, as well as user applications where they're available already. Then the Vitis IDE can then be used to develop Linux applications. And you only need to specify a domain, a Linux domain, and it can then begin building Linux applications from the templates available. So when you add a Linux domain in the Vitis IDE, it will ask you to provide a path. Oops, this is the wrong. Provide a path to the bootable image format file and several of the boot components, which are in the output directories of the Petalinux build. When the platform project is then defined in the Vitis IDE, you already have the boot components are also automatically generated there, and so you would not need to. You can specify them, but not necessarily. So the only thing you need to provide really is a Linux image. And then you can develop an app based on that Linux domain, and it can be created from the ground up or by using an available template. And then you can build it. The necessary ELF file should be generated, and then you can also debug this Linux application from within Vitis using the target communication framework. So we'll actually build an application in a little while this way as well. Now, we're going to review this a little bit as well, but now from a Linux perspective. During the previous session, we already explained the booting process of an MPSoC device, but yeah, so let's look at this from the perspective of an embedded Linux system. So as expected, it looks quite similar to the sequence we discussed during the previous session. First, the PMU releases the CSU from reset, and then enters PMU service mode where it monitors power. After the PMU releases the CSU from reset, if it is in non-secure mode, it loads the first stage bootloader into on-chip memory. If it is in secure mode, then the configuration and security unit checks to determine if authentication is required by the FSBL or the user app, and it proceeds only if the authentication check passes. Then it checks if the image has any encrypted partitions as well. After loading the first stage bootloader, the CSU goes into tampering monitoring mode. The PMU firmware also runs from PMU RAM in parallel to the first stage bootloader and on-chip memory. After the CSU has completed its actions, then the first stage bootloader starts on the application processing unit and hands off to the ARM trusted firmware, which will then be executed. The ARM trusted firmware then in turn hands off to the second stage bootloader, in this case U-boot, which executes and loads the operating system such as Linux. Linux in turn then loads the executable software and corresponding bitstream from the user. Note that the ARM trusted firmware, U-boot, and first stage bootloader all run on the application processing unit. So and note, so there's the real-time processing unit is completely unused in this particular flow. So we're going to build the Linux system shortly, and we're going to configure it to boot from an SD card. There are other options to boot from, such as QSPI, JTAG, etc. But for this session, we'll use the SD boot option. And to boot a Petalinux on hardware with an SD card, you'll need a number of files, and these files are the boot.scr file, the boot script, your image, your fit image, and the boot.bin file. So the boot script and image UB files are generated when you run the Petalinux build command, and the boot.bin file needs to be packaged. The boot.bin file is a bootloader binary file that contains the first stage bootloader, the U-boot, ARM trusted firmware, platform management unit firmware, and the optional bitstream, and it can be packaged using the Petalinux package command. Once we have these files, they need to be copied onto the SD card, but before that can be done, the SD card needs to be prepared as well, and because it needs 2 partitions. So the first partition can be a FAT partition, and this first partition contains the bootloader, the device tree, and kernel images. The second partition should be formatted as ext, as an ext file or partition, and that will contain the root fs. Once the zip file is placed on the partition, you'll need to unpack it though as well. So in order to configure Petalinux for SD card system boot, this also needs to be configured when generating or building the components in using the Petalinux config command in the image packaging configuration. So you need to make sure that we're in the project directory, we run Petalinux config, and in the image packaging configuration, you select the root file system type. Okay, due to limited time, I think available today, we won't do this, but as booting Petalinux using QSPI is very common in production environment. Let's talk about this very briefly. Petalinux also obviously allows you to boot a Petalinux image on hardware using QSPI by flashing or copying the fit image or individual images into the flash memory. So, and here are the steps involved to flash and boot this Petalinux image from QSPI. So the first thing, set the primary flash as a boot device and set the boot script configuration to load images from QSPI flash. Second step is to build the system image. The third step is to boot the Petalinux image on hardware using JTAG up to U-boot. Then make sure that your TFTP is configured in the host as well. Check or update for offsets. Check or update the offsets for the kernel and rootfs using the boots script file. Because if they don't match, the process may fail at the U-boot prompt. Step 6, set the server IP address as the host IP address at the U-boot prompt. Once it's done, detect and erase the flash memory. Then read the images from memory and write them to flash. Step 7 is to enable the SPI flash boot mode on the board, and the final step is just to reset the board, and booting should start from flash.
So, Christoph, just very quickly, whilst you're still on that slide, there has been a question that's popped through asking about boot arguments. What are the boot arguments which should be updated in the system conf.dtsi to then boot from the SD card or USB? Is that something that you could maybe touch on at the end, or
yes,
or
we'll go through building, and then maybe when we go through building, we can it might become clear when we go through the build and actually do some configurations in the Petalinux tools.
Thanks.
So yeah, we can come back to that later. So I still have a number of slides left, but we're already 40 minutes in the session, and this is now mostly around some advanced configurations, but I can talk about these while we're building the system. So let's start by building the system and get it up and running. So I need to, obviously, I now have an Ubuntu virtual machine. This is my workspace for that. So I've already set this up. So we're here in webinars, webinar 3. I have the only file I need to start building a project is the exported hardware description. Now on the right hand side, remember I did mention that Petalinux build is going to take 90 minutes to build, or an hour the first time, so we won't have that time. So I had already pre-built something, so we can kind of move to that. But so in order to start building a project, Petalinux, first command we need to do is Petalinux create -t, the name, and using a template ZYNQ. So the project's created. So I now have my directory. Here you see that this project layout has been created, the project spec with these subdirectories. So the next step is to import the hardware. And I'm going to specify the path to where the XSA file is located, which is here. And this will now open the configuration window for the first time. So if we now go back to the slide, we'll just wait for that to open. And I'll now go back to my slides. So you see, actually, no, I won't have to go back to my slide. Let's just discuss this. So here is where you can perform the initial system configuration. So you not necessarily need to configure all of them, but let's go through some of these. You can configure the Linux components you want to include in the build. Image selector is only available for the ZYNQ MPSoC devices. We obviously want to include the first stage bootloader, PMU, U-boot, trusted firmware, and the kernel. So this one's quite interesting. The Subsystem Auto Hardware Settings menu allows you to customize how the Linux system interacts with the underlying hardware. So here you've got a number of available options. The System Processor menu specifies the CPU processor on which the system runs. The Memory Settings menu allows you to select the primary system memory, which is DDR0 here for us, which is fine. Set the base address and size of that system memory, and set the U-boot text-based address offset. This impacts the memory settings in the device tree as well as the U-boot configuration files. Serial settings. This menu allows you to select which serial device is the system's primary STD in, STD out interface. So remember, we had two UARTs. We had UART 1 and 0 enabled in the hardware, so we could just leave it as UART 1, which is fine. Ethernet. The Ethernet settings menu selects the system's primary Ethernet. Once that's done, you can select to either randomize the MAC address or set the MAC address of the Ethernet. If a MAC address is programmed in EEPROM, then it will boot from EEPROM. And then if no MAC address is configured in EEPROM, then U-boot automatically configures a random MAC address. Flash settings selects the primary system's flash and sets the flash partition table. SDIO settings. This is for ZYNQ MPSoC only. It allows you to select which SD controller is the system's primary SD card interface, and we have that one. That's correct. So it's read all that information from the XSA file, obviously. And then the real-time clock settings. This menu allows you to select the real-time clock interface that is used as a primary timer for the Linux kernel. Device tree generator settings. I'm going to go back to my slides because I think it's one question has come in around, and I'm not saying this is not going to answer your question in particular, but it's pull up my slideshow again. So in this picture, you'll see the process of generating the device tree files using the Petalinux tools. When you build Linux for the first time and explore the directories, then you may have come across a bunch of these DTSI files, and it may not seem very intuitive. And trust me, for me, it's as to date still not super intuitive. So this slide explains the process and the file types a little bit more. So the device tree generator, which is part of Petalinux, reads the XSA file. And the device tree generator helps you build the hardware-specific device tree source files, as a lot of information captured in the device tree source files can be extracted and parsed from the information provided in the XSA. So the device tree generator will populate the device tree source files with as much as information as it can based on that, but you will still be expected to fill in the blanks or as adjusted as needed, and specifically when you're building custom hardware. So building device tree source files for custom hardware will always be somewhat a bit of a manual process, but at least the device tree generator can help jumpstart you to an advanced starting point. Device tree generator, as I said, is part of Petalinux, but also the Vitis unified software environment. So it's good to spend a bit of time on this because device tree, probably the Linux experts in the session here will probably know more about this than me, but this is typically where things can fall over in sort of device tree. So the device tree generator generates device tree source files with either .dts and .dts include extensions. The DTS file is a textual description of the system device tree. Usually there is a single top-level DTS file with include statements to reference separate DTSI files. This way the information can be organized in different files. One DTSI file, for instance, can be used to describe fixed hardware that is fixed on silicon, while another DTSI file can be used to describe dynamic hardware, so IP and the programmable logic. Once the DTS files are generated, these files are compiled by the device tree compiler to generate a device tree blob. The device tree compiler is open source, is an open source compiler, available part of the Linux source directory. And one way to compile the device tree compiler source code and generate device tree blob files is to build the Linux kernel. So you don't necessarily need to run the Petalinux command, Petalinux config-c device tree. And the primary use of the device tree blob is to provide itself to the Linux kernel so that the Linux kernel can be initialized to specific hardware correctly. It describes information such as the hierarchy of the hardware, addresses, size, connections, and board layout. The DTB file is provided to the kernel at the boot up stage. So the kernel startup code reads the DTB and instantiates and initializes the kernel appropriately. It understands it, system memory location, size requirements, device types, address mapping, as well as configuration options. And finally, the kernel infrastructure then binds the drivers to the devices. So that's a bit of an understanding of sort of what goes on behind the scenes. And in order to configure the device tree generator tool, we were just in that particular menu config. So let's discuss this a little bit here. So the machine name allows you to set or add a machine name. For custom boards, it's a template, and for evaluation boards, it can take a value such as the ZCU104 or ZCU106 Reveille and things. So here we are. The kernel boot arguments menu allows you to let Petalinux automatically generate the kernel boot command line settings in DTS or pass user-defined kernel boot command line settings. The device tree menu allows you to separate the programmable logic from the base DTB as well and build the pl.dtsi files. The removing PL from device tree menu allows you to skip PL nodes in your design if your design, for instance, does not depend on programmable logic IP. So here you have a list of common DTSI files generated in the output directory for the ZYNQ UltraScale Plus MPSoC device. So if I go back to our config, here we can have kernel boot arguments. So we can, by deselecting no, you can add your own boot arguments here and here. So for now, I'm going to just do them automatically. So they're all the automatic boot arguments for me in this case. So let's exit this. I'm happy with that. So BMU firmware configuration, we can set some compiler flags, untrusted firmware. The Fpga Manager, the Fpga Manager allows you to program programmable logic, the bit stream of the programmable logic through various means by the Fpga framework. So I'm not going to spend an awful lot of time on this today. So I'm not sure, maybe some people may have seen this already, but there is the ZYNQ PL programming, which explains the Fpga Manager. Because if you recall, the PL can be programmed at various stages can be done by the first stage bootloader, U-boot, or even through Linux. And it goes here through how to do this via Linux. And one way to start doing that, the Petalinux flow, is by enabling this Fpga Manager. And then you also have an Fpga utility where you can basically program the bit stream. The U-boot configuration. Let me go back to my slides here as well. The U-boot configuration option allows you to select the U-boot automatic configuration or a U-boot board configuration target. So by default, Petalinux uses the board configuration named called Other. If you want configurations from a design, select U-boot config. If you enable the U-boot DTB configuration, you can build separate U-boot DTB files with the provided design, and you can find that binary then in the images Linux directory with the name uboot.dtb. You can change the name with the U-boot DTB package name option, and if you have a DTS file to build a separate U-boot DTB, then use U-boot DTS file path to provide the DTSI files with space separation. So let's go back to configuration. I actually don't need to do anything fancy here. We'll get to this in a second. Actually, no, I wasn't finished yet. We're still in U-boot. Yes, okay. So Petalinux allows you to select the boot image storage options such as QSPI, Flash, etc. by doing the following. So from the Petalinux configuration directory, project directory, it's done by the Petalinux config command if you want to change it afterwards. So in the U-boot script configuration submenu, you have a number of options. So to append provided offsets to the memory DDR base address, select append base address to the image offsets. Petalinux then reads the DDR base address from the hardware file and appends it to the offsets provided. So this is enabled by default. So I had a question coming in about U-boot variables over the last week, actually, environment variables. So to add any U-boot environments variables that have to be executed before boot, select pre-boot environment. So this is where you can add any U-boot environment variables that you need to have executed before the boot command. To check and modify the JTAG DDR offsets, use JTAG and DDR image offsets. These are used in JTAG boot mode and also load images from flash storage to DDR memory. And to check and modify the QSPI offset sizes, use the QSPI image offsets config menu. So you have to make sure that the offset sizes do not overlap with the boot script, so the boot.scr, or the image that is actually to be imaged. So I don't need to do anything fancy here. I'm just going to leave this as is. And then we arrive at the Linux packaging configuration, which image packaging configuration, which probably is also quite common to reconfigure. And this allows you to set the following packaging configurations: the required root file system type, the file name of the generated bootable kernel image, the Linux kernel image hash function, DTB padding size, and whether to copy bootable image to the host TFTP server directory. Note that the default configuration option for Petalinux init RAM FS image is init RAM FS init RD. You can provide the name of the Yocto image recipe that's used to build an init RAM FS init RD file system in the menu config option, init RAM FS init RD. By default, it's set to Petalinux image minimal for ZYNQ 7000 devices and microblaze processors, and set to Petalinux init RAM FS image for ZYNQ UltraScale Plus, MPSoCs, and Versal ACAPs. Petalinux init RAM FS image is a small file system that's deployed into Images Linux as well. You might find there as an output, and it's but it's also packaged into the fit image as image UB, and this allows the specified image to be bundled inside the kernel image. Init ramfs init an init ramfs init RD image provides a temporary root file system for early systems initialization. So for example, when loading modules that are needed to locate and mount the real root file system. If the image specified in the configuration contains the init ramfs, then the configuration option is packaged in the image.ub file, and it's also copied into images Linux folder. And another example is for if you are in QSPI mode and you have flashed the files, it will boot up the tiny root file system and then search for the external root file system to mount, and you use that as a real root file system. In the case of SD, we're talking about the SD case here. So in my, let's maybe make that, doesn't really matter, init ramfs for now. Tiny root fs is fine. And then for the firmware configuration, give it a name here. You can change the name, where it will show up, etc. Some Yocto settings. I won't go too much into detail here. So this is then the first time you go through the configuration, and then this won't take too long. So the next, you could, should you desire, so you could build the device tree individually. You could build U-boot individually, but there's not, I don't have any, we'll open it up, but I don't have any specific configurations. But for the root FS, for instance, you can customize the root file system. But what we'll do now is, where is my, I've got a few. Why don't we create an application as well, and then we can add it to the root file system. Create apps minus name. And I'll see it has now created an application in this directory. If I have a look what's in there, we have a README file here. And we have a template, a make file, and a C file. If I now open that, have a look what's in there. It'll just be pretty basic application. Hello world. Okay. So I have created the application. I've not added it yet to the root file system, but we can also do that while we configure the root file system. And here we have it identified a new app. So if I want to add it, I type Y to add it and then exit. So this should now be, when Petalinux now builds, I should find that application in the user.bin directory. But obviously we can also add packages. You can customize your root file system as per your preferences. So what I would like to add, for instance, here is, because we've added an Ethernet MAC, so we are going to see Ethernet up and running in a few minutes. I want to, for instance, add enable ETH tool, or what else? No, it's a little bit. No, not net TCP dump. So obviously you find a lot of packages, so whatever you wish to add. So the one thing you need to check though, it's enabled by default, so I wouldn't worry about it, but where is it again? It should be enabled by default, and that's the Tcf agent. So if you want to debug an application or run an application where Vitis communicates with Linux, that the Linux Tcf agent needs to be enabled. But see, by default, it's always enabled. But again, for development, you can have make, you can install make, you can install add packages as you desire. So the only thing I'm really interested in at the moment is Ethernet, ETH tool, TCP dump, and maybe an application, and that's kind of it. Save that, build the root file system, and then you can also configure the kernel. This might already take a bit longer. So the kernel is, obviously you can enable device driver, modify device driver settings, and things. Let's see if we can open that. This might now take a little bit of time, I think. So once the kernel is configured, then the next command to execute would simply be Petalinux build, and that's going to take a little bit of time. The first time, because the second time, because it's an incremental build, it'll be a bit faster, and then the final step would be to package the image. So I already have the command here so that I don't have to do that again. So it's created my bootable image with all the components in it. So I've, as I mentioned already, I've cheated a little bit. So in images Linux, you'll find everything you need. So the boot.bin contains a bunch of these files which are in this directory, but then you also have your boot script and the image. So I've already copied the boot.bin, the boot SCR, and image.ub onto my SD card. I've already placed the root file system and unpacked the root file system in the partition, in the ext partition of the root file system, and so I can pretty much just boot it now. So if I turn that on, I'm going to turn on the evaluation board. Scroll back up, see all the steps. First stage bootloader, the untrusted firmware, then it hands off to U-boot, and then it starts the kernel, loads the kernel. And I've got an Ethernet cable connected, so no IP address assigned yet, but because I've added eth2 in the root file system, I can actually have a look. And yes, it's detected. If I unplug cable, links down, that makes sense. Plug the cable back in, should come back up. And then in user bin, I should have the application. Okay, that's not the one I want. What happened here? So this is my pre-built image sort of thing. Maybe I hadn't enabled it. Let's check in the root file system. Oh, okay, I had not enabled it. So, okay, that's why it's not been added. So that's fine. I mean, okay, it's not fine, so I can't show the hello world, but there is another application here. If I just run that, then I've got my Linux application. So this is a platform power management demo. Let me just reboot the system, which is fine. So while this boots, now what I'd like to show you is sort of the interaction between Linux, between the Linux, Petalinux environment and Vitis. So let's start by the Ethernet connection needs to be up. Oh, here it's up. Wait for the P address. Okay, 71. The reason why I need that IP address is because that target communication framework, I can set up my Linux agent. So if I set up my Linux Tcf agent here, the IP address 71 is my connection. Okay, I can talk to Linux via Vitas. This is great. So now that we've got a connection with the board, with Linux, or from within Vitas, what we can now do is, if you wish to build a Linux application from this environment, which might be easier for debugging as well, we just create a new domain first, which is based on Linux. Now it is a Linux domain. And here it's asking for the bootable image format file. And this is now where you typically point to this output directory, where you have your bootable image, your bootgen, your BIF file. This is how you can import that. Because I've actually copied that on somewhere on Windows because it's a virtual machine. So anyway, so that's my bootgen. The boot components directory, it isn't images Linux. And for that, this is optional, don't really care about that for now. So if I now create a domain, and build it, I can now add an application, a Linux application belonging to that domain. So as per last week, we can file new application project. We're still in the same platform project, say, because remember that platform project used the same XSA file. Hello. We will create a new system project into that domain. Select the Linux domain, the root file system. I don't think that's necessary, but you could just point to that. The sysroot, this is, you can, if you've built, if you recall, with the now let me just pull up my slideshow again. With the Petalinux package --sysroot, it would install the sysroot for the Vitas platform, where you can specify the installer path and also the install directory path. So we won't do that now, which is okay. But let's click next. And it will also offer a number of templates. Let's call it Linux Hello World, also, which is fine. If I click the hammer and build. And now I can, just as per for any normal application, any standalone application, I can create a new debug configuration. But this will now, I'm going to create one for it. And this will now a Linux application debug, and the connection is the Linux Tcf agent. Fine, click debug. It will hit the main breakpoint. And now we've run this application from within Vitas on Linux. So here, obviously, this is taking a bit of time to build. So I think the last thing I wanted to, what we were getting at was maybe the kernel. Faster here in the pre-built and the pre-built. area. But I think I think we're sort of at the end of the webinar. So if there are any questions at this stage, then I suppose we're happy to take them, and we'll see. Hopefully, we can answer them for you.
So one that's come through just now, Christoph, is about adding third-party Linux applications.
Okay,
how would one add a third-party application that's not in a Petalinux configuration?
Okay, so let's go through the slides then. If everyone's happy to hang on for another 5 to 10 minutes, then we can. This is where I thought it would run over, but yes, you can customize the root file system as per preference. So apart from adding common packages, you can also add your own pre-compiled library and applications. I suppose that's the question, right? Which are built outside the Petalinux environment. So if a library or an application is developed outside Petalinux, you just need to add it to the Petalinux root file system. And what you need to do in that case is create an application template to allow the copying of the existing content to the root file system. You need to ensure, though, that the library code has been compiled for the desired Petalinux target architecture. And then you can begin the process of adding your pre-built library or application to the target. So step one is to create an application template using the Petalinux create command. And in this case, we'll assume that the pre-built library here is mylib.so. The the dash enable, double dash, isn't it? Yes, double dash enable option enables the application in the root file system. Step two is then you go into that particular directory, and step three is to replace the existing library there with your pre-built library. Step four, though, you need to edit the recipes file, the .bb file, for including the library and making the required changes, as is shown here. Step five is to build, again, as per usual, the usual flow, and package the library in the root file system. And then you should find your pre-compiled library in this directory. So it's the same. It's similar to a pre-built library. If you've developed an application out of Petalinux, you must add it to the root file system. And also here you do that by creating an application template. And then you move to that directory and you have to replace that into with the pre-built MyApp, and then build again. So these are pre-built libraries and applications, but you can also add a custom library and application. So steps 1 and 2 are the same as before in terms of creating an application. Here it's called libsample by using the Petalinux create command. Then you change into that directory. Step 3 is to edit the recipe file, the libsample.bb, by using in this directory shown here to reflect the changes as shown in the figure. Step 4 is to add the source file as per your requirements in the directory given here. And if your changes require a header file, or you can create or add your header file as well. Step 5 is to make the corresponding changes in the make file in the figure located here. And then step 6 is to build again. Kernel modules, you can also create and add custom modules in the root file system. So kernel modules are pieces of software that can be loaded or unloaded on demand, and that extend the functionality of the kernel so that you don't need to reboot the system. And in order to do that, you can create a user module. So rather than creating an application, in this case, you create a module using Petalinux create-t modules. Here it's called my module. Step 2 is also to change in that directory that had been created. Step 3 is to edit or replace the created default code to the custom module. Step 4 is to modify the recipe file for the module if the source code is split into more than one file. And then again, step five and 6 up to build and to verify that they exist. So it's typically, it's just a case of creating an application template for precompiled libraries and applications that are built outside Petalinux. Does that answer your question?
Yes, I think it did. I did get some feedback. Yes, yep. Thanks very much. Yep.
So what I can do, we can share these slides with you because it's kind of nice to have a little bit of a flow, like where you can. I agree. This is kind of a nice view to follow the steps. So the final thing I wanted to show you here was the kernel configuration. So obviously, if you have specific device drivers, you go into kernel configuration, etc. So you can have CPU power management option where you enable or disable idle support or frequency scaling support, etc. Now, I'm not an expert on Linux kernels by all means, so but obviously this is where you can customize the kernel as well. So, are there any further questions?
So yeah, well, I have had a few requests. Copy of the slides.
Okay.
So I think, yeah, certainly we'll talk internally about the best way to manage that.
Okay.
And obviously, you know, that Christoph may need some opportunity to, you know, to tidy things up. You know, if he's got notes there that you know, don't need to be there and things like that. But also we're quite limited, you know, we'd have to send some emails out to folks directly. That might be an option. So we'll have a chat about that internally and see what we can do. One of the things that maybe not everybody's aware of either, Christoph, is some of the ZYNQ wikis and GitHubs and things that you have found particularly useful. Just wondering if that's something that you can either share now, or we can maybe share with people in terms of you know, sending out a URL as well. You know, we could probably add that maybe even in the chat window or something like that. And then, yeah, I think the other thing is some people have said that they've not received the recorded sessions. So what I'll do now is I'll actually pop the recorded sessions URLs in the chat window as well, just so, you know, folks can grab it from there. But yeah, there should have been some emails that have been sent out. I know pretty much everybody that's registered will have been sent the email. But in the off chance that you haven't received it, then we can post it in the chat window just now. Just give me 2 seconds. Yeah, that's a very good point. If you can maybe check your junk mail to make sure that, you know, it didn't get filtered into your junk mail as well, because some folks have actually just responded saying that they found it in the junk mail. So let me just very quickly. Just while I'm getting the URLs to post in the Q&A window, Christoph, another question that's popped up here is, can you briefly touch on the nuances in the process for building and deploying Petalinux for a microblaze and developing apps for that in Vitis. Sort of a brief kind of discussion on what, some of the differences, I guess, between that and using microblaze.
Gosh, it's been a while since I used micro, but let's okay, so let's go in. Okay, so what happened here? Am I stop sharing? No. Stop building. So there are not that many differences. I suppose the whole flow is kind of the same. Let me pull up my slides again. So, or if we a microblaze does not, for instance, the steps to build a project for a microblaze is pretty similar, right? So you can Petalinux create depending on the template. So that's all relatively template microblaze. So that's all. The main difference on a microblaze, I suppose, is it's ZYNQ is the boot component. The microblaze is not a heterogeneous device, so you will not have things such as ATF, such as platform management firmware, such as a first stage bootloader. I mean, so those are all components that will not be built. So the bootable image format and some of the terminology will be different, although the flow is typically the same. So I suppose can't really build this now.
Well, I mean, what we could, maybe we can take this as a separate session,
yes.
For those people that are more interested in, rather than using a ZYNQ UltraScale Plus, want to use a a 7 series or an Arctics or something like that. Perhaps we could do a slightly different session that just focuses on microblaze, or for that matter, those people that actually want to use an UltraScale Plus and include the microblaze is possibly something else, which kind of brings me on to a couple of things. There's one more question here, Christoph. That's does Petalinux run on all cores, or does it need to be set up so it can?
Okay, I see the question here. On all, are you talking on the cores on the MPSoC? No, Petalinux, sorry, on the cores on. No, you need to set that up, I think. On your operating system, referring to, right? No, you need to set that up. I would need to refer to the user guide myself now, but I think you need to set that up. But just off the top of my head, I'm afraid I can't answer that question right now. So for the people who are not familiar with Petalinux yet, user guide 1144 is the magic bullet. I mean, this is where everything I've gone through today you'll find in here as well, and probably in more detail. So probably the best place to search is Petalinux installation requirements for that question. That would be good. Thank you.
Yeah. So that's for the microblaze sort of.
Yeah. No. Okay. So
Sessions. Yeah.
In short, I think the process for building and deploying will be very similar. It's just the nuances will be in the different boot components because the MPSoC is a much more complex device. But yes, as mentioned, we can touch on that separately.
And I guess, yeah, if so we, you know, at the very outset of this, when we sort of asked for some feedback from folks, you know, on what people would like to see, we did get a number of requests for things like a session on using the logic analyzer, and you know how you might do some debug and things like that between ZYNQ UltraScale Plus, but also you know with programmable logic fabric. So that's possibly another session that we can set up. And then another one that we have had a request for as well is oh, I've just gone blank. Setting up debug and timing constraints, and you know how to some of the processes to go through in terms of you know what you might look to do to help fix some of the timing errors. So those are a couple of other sessions that we might look to do in the near future. So if there's anything else, you know, we'd love to hear from you. Just going through these questions, so I think we've got most of these either answered live or one or two that we may need to come back to you on. So at this point, yeah, look, if there's anything else, certainly reach out. You can reach out to either myself or Ali. Christoph's going to be sloping off for a bit of R&R for a couple of weeks. But certainly if you have questions, please come through to myself and Ali, and we'll look forward to talking with each of you guys in the near future. Thanks. Thanks very much for your attendance. Bye for now.
Thanks, everyone.